Last week's storm was just a warning. That's not dramatic language. That's not an exaggeration designed to grab your attention. It's the reality scientists are confronting right now as they continue monitoring this active region. While the world moved on from those spectacular auroras and the brief disruptions they caused, the source of that activity remains. The sunspot that blasted our planet with a powerful surge of energy is still out there, still aimed, still active, and it has the potential to produce another eruption. This represents an ongoing space weather situation worth understanding. The event that lit up skies across the globe, that sent ripples through our technological systems, that reminded us how connected we are to our star that wasn't a one-time occurrence. It was a demonstration of power from a region on the Sun that remains magnetically active. Right now, as you're watching this, that same sunspot sits on the face of the Sun, positioned facing Earth, displaying ongoing magnetic complexity, and being monitored closely by scientists who understand what it's capable of. They've seen this pattern before. They know what comes next isn't always predictable, but it's absolutely possible. Most people saw the headlines about last week's solar storm, watched the videos of auroras dancing across unusual latitudes, maybe noticed a few minor disruptions in satellite communications or GPS accuracy. Then they moved on. Life continued. The Sun rotates after all. Sunspots come and go. The concern passes, right? Except this time, something different is happening. This sunspot didn't rotate away as expected. It didn't fade into dormancy after its initial blast. Instead, it remains in what scientists call the Earth-facing position, the most significant position for Earth-directed space weather. And the monitoring equipment, the satellites positioned between Earth and the Sun, the observatories scanning solar activity every single day, they're all showing the same thing. This region is still capable, still active, still loaded with the kind of magnetic energy that produces exactly what we witnessed last week. Stay with me for the next several minutes. We're going to uncover something most people don't realize is happening right now above our heads. We'll explore what actually occurred last week, why it mattered more than casual news coverage suggested, and most importantly, why the story isn't over. You're going to understand what makes this particular sunspot different from the dozens that appear and disappear on the Sun's surface every month. You'll learn what scientists are seeing in their data that keeps them monitoring this region around the clock. And by the time we're done, you'll grasp why this isn't fear, isn't speculation, but rather careful observation of a real ongoing situation that could unfold again at any moment. Can this sunspot fire another powerful blast toward Earth before it rotates out of range? The Sun isn't a static, unchanging sphere of light in our sky. It's a dynamic, churning ball of plasma with a magnetic personality that shifts and erupts in ways we're still learning to predict. For most of human history, we were blissfully unaware of these eruptions. They happened, they reached Earth. They created beautiful auroras and life went on. But we don't live in that world anymore. Our civilization now depends on satellites for communication, navigation, weather forecasting, and financial systems. Our power grids stretch across continents, connected and interdependent. Our technology has made us more capable than ever before, but it's also made us more aware of our relationship with our star. When the Sun releases a powerful blast of magnetic energy and charged particles directly at Earth, it's not just a light show anymore. It's a test of our infrastructure, our preparedness, and our understanding of the space environment we inhabit. What happened last week was significant. Scientists classified it as a severe geomagnetic storm, a level that occurs several times per year during active phases of the solar cycle. It wasn't the strongest possible storm those exist on a scale we've only experienced a few times in recorded history, but it was strong enough to cause concern, strong enough to trigger alerts, strong enough to remind everyone watching that we're not as insulated from space weather as we sometimes assume. And here's what makes the current situation so compelling. The source of that storm hasn't moved on. It's still there, still facing our planet, still holding magnetic energy, still capable of producing another eruption that could be just as powerful, or potentially even stronger. If you found this topic important, if you want to stay informed about something that affects our technology, our infrastructure, our connection to the space around us, then hit that like button right now. Subscribe to this channel so you don't miss updates on this developing situation or other science stories that matter to your daily life. And drop a comment telling me where you're watching from. I'm curious to know how many different parts of the world are following this story together. Because this isn't just about one country or one region. When the Sun fires at Earth, we're all in the path together. Now, Let's go back to last week and understand exactly what happened, because that's the foundation for understanding why what's happening right now matters so much. Last week, the Sun reminded us of the dynamic relationship between Earth and our Sun. It wasn't a gentle reminder, it wasn't a subtle nudge, it was a powerful demonstration that reached across the void between our star and our world, travelled through space at speeds that challenge comprehension, and delivered an impact to Earth's magnetic field that reverberated through our technological systems and painted the sky with light that shouldn't have been visible so far from the poles. If you missed the details, if you only caught fragments of news coverage between other headlines, then you missed the full scope of what actually occurred. So let's walk through it together, step by step, because understanding last week is essential to understanding why this week matters even more. It started with an eruption. Not just any eruption, but a significant release of magnetic energy from a specific region on the Sun's surface, a sunspot that had been growing, developing complexity, building tension in its magnetic field structure. When that tension finally released, it happened in a way that solar physicists recognize immediately as significant. The eruption sent a massive wave of plasma and magnetic field out into space, a structure called a coronal mass ejection. Think of it like the Sun coughing out vast amounts of charged particles in a specific direction, and that direction unfortunately was directly toward Earth. The eruption happened quickly, energetically, with enough force to send this cloud of solar material racing across the distance between the Sun and Earth at remarkable speeds. Under normal conditions, light from the Sun takes just over 8 minutes to reach Earth. That's the baseline. The speed of light is absolute, unchanging, the fastest anything can travel through our universe. But this blast of particles wasn't travelling at light speed. It was much slower, bound by different physics, driven by the magnetic structure embedded in the plasma cloud. Still, it was fast by any earthly standard, fast enough to cross the vast distance between the Sun and Earth in roughly a day. That's the critical number. When scientists detected the eruption and began calculating its speed and trajectory, they knew they had approximately 24 hours to prepare. 24 hours to alert satellite operators, to notify power grid managers, to inform airlines about potential communication disruptions, to warn anyone whose systems might be vulnerable to what was coming. You might think a day's warning sounds like plenty of time. In some ways, it is. It's infinitely better than the zero warning our ancestors had when solar storms struck in centuries past. But in practical terms, for our modern, interconnected technological society, it's actually a remarkably narrow window. Satellites can't be quickly moved out of harm's way. Power grids can't be completely shut down without massive consequences. The best we can do is prepare, monitor, and respond. So that's what happened. Space agencies around the world tracked the incoming cloud. Scientists analysed its magnetic structure, trying to determine how severe the impact would be when it arrived. Operators of critical systems went on alert, ready to respond to whatever came next. Then it arrived. The blast of solar plasma struck Earth's magnetic field, compressing it, distorting it, pumping enormous amounts of energy into the magnetosphere, the protective magnetic bubble that surrounds our planet. When that happens, when all that energy gets injected into Earth's magnetic environment, it has to go somewhere. Some of it gets channeled toward the poles, where it interacts with our upper atmosphere and creates auroras. But this wasn't a normal aurora event. The storm was powerful enough to push those auroras far beyond their typical range. People in regions that rarely or never see the northern lights suddenly found themselves watching curtains of green and red light dancing across their night sky. Social media filled with photos and videos from places that had no business hosting an aurora display. It was beautiful, certainly, but it was also a visible symptom of just how much energy was being dumped into Earth's magnetic field. While people were outside photographing the lights, other effects were happening that received less attention but mattered just as much. Satellites orbiting Earth felt the storm's impact. The increased density of particles in the upper atmosphere creates drag that affects satellite orbits. Communication signals passing through the charged, disturbed layers of the atmosphere experience disruptions, delays, degradation, temporary losses. GPS accuracy suffered as the signals travelling from satellites to receivers on Earth got distorted by the magnetically disturbed atmosphere. Airlines rerouted some polar flights to avoid communication blackouts and increased radiation exposure at high altitudes. Power grid operators monitored their systems carefully, watching for signs of induced currents that could damage transformers. This is what a severe geomagnetic storm looks like in our modern world. It's not just pretty lights, it's a complex cascade of effects touching multiple systems we depend on daily without thinking about them. And this storm reached a classification level that scientists designate as severe, not the most extreme category possible, but definitely in the range where significant impacts occur. The last time we experienced a storm at this level, it caused similar disruptions. The time before that, the same pattern. We know what these storms can do because we've experienced them before, measured them, documented their effects, learned from them. But here's what made last week's storm particularly noteworthy, beyond its immediate effects. It came from a sunspot that scientists had been watching with interest, a region that had already shown signs of significant magnetic complexity. When you study the sun professionally, you learn to recognize which sunspots are likely to erupt and which are probably going to stay quiet. This one had all the characteristics of an active, magnetically complex region, and when it erupted, when it proved those concerns justified, scientists didn't just analyze the impact on Earth, they kept watching the source. Because one of the most important things to understand about sunspots, about active regions on the sun, is that they don't typically erupt just once and then go dormant. They can fire multiple times. They can produce several eruptions over the course of days or weeks. History is full of examples where a sunspot produced one significant eruption, then followed it up with another, and sometimes another after that. So while the headlines focused on the aurora photos, while the public attention moved on to other news, scientists kept their instruments trained on that sunspot. They continued analyzing its magnetic field structure. They monitored for signs of new energy building, new tension developing, new eruptions preparing to launch. And what they saw didn't give them any reason to relax. The sunspot remained active, it remained complex, it remained capable, and crucially, it remained in the Earth-facing position still aimed directly at our planet. Last week's storm wasn't the end of the story. It might have been just the opening act. That brings us to where we are now, to the situation unfolding as we speak, to the reason scientists haven't stopped monitoring this particular region of the sun. Because understanding what happened last week is the foundation. Understanding that this sunspot is still there, still active, still pointed at Earth, that's the story we need to explore next. To understand why scientists are still concerned, why the monitoring hasn't stopped, why this situation feels different from the dozens of solar events that happen throughout the year, we need to talk about the sunspot itself. Not as an abstract concept, not as a technical term you've heard in passing, but as a specific identifiable region on the sun's surface with characteristics that set it apart from most other sunspots that appear and fade throughout the solar cycle. So let's start with the basics and build up from there, because once you understand what a sunspot actually is and why some are more dangerous than others, the current situation becomes much clearer. Imagine the sun's surface as a churning, boiling mass of plasma matter so hot it exists in a state between gas and liquid, where electrons are stripped from atoms and everything is electrically charged. This plasma is constantly in motion, driven by the massive heat and energy being generated in the sun's core. And running through all of this, woven throughout the entire structure of the sun, are magnetic fields. These aren't gentle static fields like the simple magnets you played with as a child. These are powerful, dynamic, constantly shifting magnetic structures that get tangled and twisted by the sun's rotation and the churning motion of its plasma. A sunspot forms when these magnetic fields become so strong, so concentrated in one region, that they actually inhibit the normal convection process that brings heat from the sun's interior to its surface. The result is a patch on the sun's surface that's cooler than its surroundings, still incredibly hot by any earthly standard, but cooler relative to the rest of the sun. That cooler region appears darker when we observe it, which is why we call them sunspots. They're not actually dark, they're just less bright than everything around them. But here's what matters. That concentration of magnetic field, that twisted, complex structure of magnetic energy, that's what makes a sunspot potentially eruptive. Because those magnetic fields can snap, can release, can explosively reorganize themselves in events that send enormous amounts of energy and material blasting off the sun's surface and out into space. Not all sunspots are created equal. Some are small, simple, magnetically straightforward regions that appear, persist for a while, and fade away without ever producing anything notable. They're like gentle hills in a landscape present, yes, but not particularly threatening. Others are different. Some sunspots grow large, develop complex magnetic structures with multiple poles interacting in unstable configurations, and show all the signs of being loaded with energy that wants to release. These are the ones that get special attention from scientists, the ones that get tracked carefully, the ones that appear in the briefings and alerts that space weather forecasters issue. And the sunspot responsible for last week's storm, the one that's still there, still facing Earth right now, falls into that second category. Scientists track sunspots with designation numbers, giving each active region a unique identifier as it appears and rotates across the face of the Sun. The sunspot we're discussing appeared in mid-January, was assigned its tracking number, and immediately caught attention because of its characteristics. It wasn't just present, it was prominent. It grew quickly, developing into a large magnetically complex structure visible even in basic observations. When scientists analysed its magnetic field configuration, they saw exactly the kind of setup that historically precedes eruptions. Multiple magnetic poles in close proximity, fields twisted and stressed, energy storage building in the structure. All the warning signs were there, and then it did exactly what those warning signs suggested it would. It erupted. It released that built-up magnetic energy in a powerful event that sent a coronal mass ejection directly toward Earth. That was last week's storm. That was the event that created those spectacular auroras and caused those technological impacts we just discussed. But here's the critical point, the piece that elevates this from a past event to an ongoing concern. That eruption didn't deplete the sunspot's energy. It didn't resolve the magnetic complexity. It didn't transform the region into something simple and harmless. When scientists continued monitoring after the eruption, they could see that the sunspot remained active, remained complex, remained capable of erupting again, and it still had time left in the most dangerous position possible facing Earth. Think about why that position matters so much. The Sun rotates, taking roughly a month to complete one full rotation as viewed from Earth. That means any given point on the Sun's surface spends about 2 weeks facing toward Earth, and 2 weeks facing away as it rotates around the backside of the Sun. For space weather purposes, we really only worry about the Earth-facing side. An eruption on the far side of the Sun might be just as powerful, might release just as much energy, but it's not heading in our direction. It's blasting off into space in some other direction, posing no concern for Earth-based systems. But an eruption from the Earth-facing side is a different story entirely. That's when the trajectory matters, when the path of the eruption could intersect with our planet, when we need to pay attention. This sunspot appeared on the Earth-facing hemisphere. It erupted while aimed at us, and crucially even after that eruption. It remains in that Earth-facing position with enough time left before rotation carries it around toward the far side. That's the window scientists are concerned about. That's the period during which another eruption could reach Earth, could cause impacts similar to or potentially greater than what we experienced last week. The clock is ticking on that window. Every day that passes is one day closer to the sunspot, rotating out of the Earth-facing zone. But until that happens, until it's pointed away from Earth, the possibility remains very real. What makes this sunspot special isn't just its current position, or even its past behaviour. It's the combination of factors that mark it as a region worthy of continued careful attention. Its size, its magnetic complexity, its demonstrated ability to produce significant eruptions, its ongoing activity, and its current Earth-facing location. All of these elements together create a situation that scientists recognise as potentially significant. They've seen this pattern before in other active regions that produced multiple eruptions over their lifetime. They know that one eruption doesn't necessarily mean the show is over. They understand that the most active sunspots can fire repeatedly, sometimes with increasing strength as they develop and evolve. So when you hear that scientists are monitoring this sunspot, that space weather forecasters are keeping it in their briefings, that instruments continue tracking its magnetic field structure, and any signs of new activity, this is why. Not because of speculation or sensationalism, but because of recognition. Recognition of a pattern they've observed before. Recognition of characteristics that historically precede significant space weather events. Recognition that the Earth-facing window hasn't closed yet, that the sunspot remains capable, and that preparation means watching carefully for any signs that another eruption is building. We're past the point of wondering whether this region can produce a powerful eruption. We know it can because it already did. The question now is whether it will do so again before rotating out of Earth's line of fire. And to understand how likely that is, we need to look at what's keeping this sunspot in position and what scientists are seeing in their real-time observations. That's where our journey takes us next. Here's where the story takes its most significant turn, where the past event transforms into a present concern. where what happened last week becomes directly relevant to what might happen in the coming days. Because the assumption most people make, the natural expectation after a solar storm passes, is that the danger has moved on. The sun rotates. Sunspots shift position. What was facing Earth yesterday won't be facing Earth tomorrow. The threat window closes. We move on, except this time that hasn't happened yet. And that single fact changes everything about how scientists are approaching this situation. Let's establish what's actually occurring right now as you're watching this. The sunspot that produced last week's eruption, that magnetically complex, demonstrably powerful region we just discussed, is still positioned on the Earth-facing hemisphere of the Sun. Not on the edge, not rotating away into safety, but still well within the zone where an eruption would be aimed directly at our planet. That's not speculation or projection. That's observable fact, confirmable by anyone with appropriate solar observation equipment. The sunspot is there, it's visible, it's trackable, and it hasn't rotated out of the Earth-facing zone yet. To understand why this matters so much, you need to grasp how solar rotation works, and why timing is everything in space weather. The Sun doesn't rotate like a solid object, it's a ball of plasma, so different latitudes actually rotate at slightly different speeds. But on average, from our perspective on Earth, the Sun takes about 27 days to complete what we perceive as one full rotation. That means any given spot on the Sun's surface spends roughly 13 to 14 days facing toward Earth before rotating around the backside, then another 13 to 14 days on the far side before rotating back into Earth view again. For space weather monitoring, we focus intensely on that Earth-facing period because that's when eruptions matter to us. That's when the trajectory becomes relevant. That's when space weather from that region could affect Earth. Active regions, the official term for sunspots and their surrounding magnetically complex areas, typically appear on the Sun's eastern limb first, the edge where new features rotate into view. They then track across the face of the Sun over the course of roughly 2 weeks, passing through the central zone where they're most directly aimed at Earth, before disappearing around the western limb and rotating out of view. Throughout that journey, scientists monitor them continuously, tracking their development, their magnetic evolution, any eruptions they produce. The most concerning period is always the middle portion of that transit, when the region is centered on the disk of the Sun as we see it, when an eruption would travel the most direct path toward Earth. The sunspot we're tracking right now erupted while it was in that central zone. That's why last week's storm reached Earth so directly, so powerfully. The trajectory was optimal from the Sun's perspective. If you're going to fire something at Earth, that's exactly the position you want to be in. And here's the critical discovery that transforms this from past event to ongoing concern. After that eruption, the sunspot didn't suddenly speed up its rotation. It didn't magically jump ahead and rotate safely away. It remained in the Earth-facing hemisphere, still within the zone where another eruption would have a direct shot at our planet. Days have passed since the initial eruption, yes. The sunspot has rotated somewhat, moved across the face of the Sun as expected, but it hasn't yet reached the western limb. It hasn't yet rotated out of threatening position. The window is still open. Scientists can calculate with reasonable precision how much time remains before a given active region rotates out of the Earth-facing zone. It's not perfect, the Sun's rotation has its irregularities, and the exact position matters, but the timeline is generally clear. For this particular sunspot, as of late January 2026, any monitoring indicates it remains in Earth-facing position, with approximately 35 days remaining in this window in Earth-facing position, before rotation carries it around the Sun's western limb and onto the far side. Several days where an eruption would still matter. Several days where scientists need to maintain their vigilant monitoring. Several days where the possibility of another storm remains very real. Think about what that means practically. Right now, at this moment, there's a region on the Sun with proven capability to produce significant eruptions. Still aimed at Earth, still magnetically complex, still active. It's not a theoretical threat. It's not a distant possibility. It's a present reality being tracked in real time by space weather monitoring networks around the world. Every day, multiple times per day, instruments observe that sunspot, analyze its magnetic field, look for signs of new activity or imminent eruption. Every day, forecasters assess the latest data and determine whether the threat level has changed, and every day that passes without an eruption is one day closer to the sunspot rotating into the safe zone where we don't have to worry about it anymore. But we're not there yet. That's the key point. The window hasn't closed. And while some people might think of this situation as the danger slowly fading away, scientists who study solar activity know that's not how active regions work. They don't necessarily become less dangerous as time passes. Sometimes they do. Sometimes an eruption releases enough magnetic energy that the region settles down and becomes relatively quiet. But other times, the opposite happens. Sometimes an eruption is just the first sign of a particularly active period. Sometimes the magnetic complexity continues building even after an eruption. Sometimes the strongest eruptions come after smaller precursor events. Historical examples reinforce this understanding. Scientists have documented numerous cases where an active region produced one significant eruption, then followed it up days later with another eruption that was equally powerful or even stronger. They've watched sunspots fire multiple times as they crossed the Earth-facing hemisphere, creating a series of impacts rather than a single isolated event. The pattern is well established in the scientific literature. One eruption doesn't guarantee more are coming, but it absolutely doesn't rule them out either. It's evidence of capability, of energy storage, but also of magnetic instability, and all of those factors can persist well after the initial eruption passes. So when you combine proven capability, we know this sunspot can erupt powerfully because it just did with ongoing opportunity. It's still aimed at Earth. You get a situation that demands continued attention. Not panic, not fear, but professional, measured, careful monitoring. Scientists aren't raising alarms unnecessarily. They're simply doing what their training and experience tell them is appropriate, watching an active region that has shown itself capable of producing significant space weather events, and remains in position to do so again. They're tracking the timeline, noting how many days remain in the Earth-facing window. They're analysing the magnetic field data for any indication that new energy is building toward another eruption. They're keeping space weather forecasts updated so that anyone who needs to know satellite operators, power grid managers, airlines, communication networks has the latest information about the ongoing situation. This is the reality as we stand right now. The sunspot is there. It's active. It's aimed at us. And the clock is ticking down on the window during which another eruption would matter. Each day that passes brings us closer to the point where rotation carries the region out of direct Earth-facing position, and the immediate concern diminishes. But until that happens, the situation remains live, remains relevant, remains worth paying attention to. And what scientists are seeing in their current observations, the data flowing in from monitoring instruments, the signs they're watching for, that's what we need to explore next to truly understand whether another eruption is likely, possible, or actively building right now. Now we arrive at the heart of the scientific question, the core concern that keeps space weather forecasters focused on this particular sunspot even after last week's storm has passed. Could it really erupt again? Is that a realistic possibility, or just theoretical speculation? And if it is possible, what would the signs look like? What are scientists actually seeing when they analyse this region? To answer those questions properly, we need to understand something fundamental about how sunspots work, how magnetic energy behaves on the sun, and what history teaches us about active regions that produce multiple eruptions. Let's start with a crucial concept that isn't always obvious to people who don't study solar physics professionally. Magnetic energy doesn't just disappear after an eruption. When a sunspot releases a coronal mass ejection, when it fires that blast of plasma and magnetic field into space, it's expending energy, yes. But it's not necessarily depleting its entire energy reserve. Think of it like a battery that discharges but isn't empty, or a spring that releases tension but remains compressed. The magnetic field structure that created the eruption is still there, still embedded in the sunspot's complex configuration, and as long as that complexity persists, as long as magnetic fields remain twisted and stressed and interacting in unstable ways, the potential for another eruption continues. This is one of the most important things to understand about solar eruptions. They're not random acts of nature occurring without pattern or predictability. They're the result of specific magnetic configurations reaching critical instability. When you have multiple magnetic field lines tangled together, when opposite magnetic poles get pushed into close proximity, when the normal configuration of the sun's magnetic field gets twisted beyond a certain threshold, something has to give. The system finds a way to release that tension, to reorganize itself into a more stable configuration. That release is what we observe as an eruption. But here's the key. One release doesn't necessarily resolve all the magnetic complexity. The region can remain unstable, the fields can remain tangled, the energy can continue building toward another release. Scientists have studied this pattern extensively by watching active regions throughout their lifetimes. They've documented cases where a single sunspot produced multiple significant eruptions over the course of days or even weeks. The historical record is full of examples. During particularly active periods of the solar cycle, some sunspots become prolific producers of eruptions, firing repeatedly as they rotate across the face of the sun. Each eruption releases some energy, but the magnetic complexity persists, continues evolving, continues building toward the next release. It's not unusual. It's actually quite common among the most magnetically complex active regions. What makes a sunspot likely to erupt multiple times? Scientists have identified several key characteristics. First, size matters. Larger active regions simply have more magnetic flux, more total energy stored in their field structures. They have more capacity to produce multiple eruptions without exhausting themselves. Second, magnetic complexity is crucial. Regions with simple, straightforward magnetic configurations, just a clear north pole and south pole, tend to be relatively stable. But regions with multiple poles, with magnetic fields woven into intricate patterns, with evidence of what scientists call magnetic shearing, where field lines slide past each other building tension, those are the regions that erupt repeatedly. Third, the evolution of the region over time tells you a lot. Is it growing? Is its magnetic field becoming more complex? Is new magnetic flux continuing to emerge from below the sun's surface? All of those are signs that the region remains active, remains energized, remains capable of producing more eruptions. Now apply those criteria to the sunspot we're tracking. It's large, not the biggest on record, but definitely substantial in size. Its magnetically complex observations of its field structure show exactly the kind of multipolar, twisted configuration that scientists associate with eruptive activity. It demonstrated its capability by producing a significant eruption already. And critically, monitoring since that eruption indicates the region hasn't simplified. It hasn't settled into a quiet, stable state. The magnetic complexity persists, the energy remains, the potential continues. But let's go beyond general characteristics and look at what actually happens before an eruption. Because that's what scientists are watching for right now. Before a sunspot produces a coronal mass ejection, certain changes typically occur in its magnetic field structure. The field becomes more stressed, more twisted. Measurements show increasing magnetic shear, that sliding motion between adjacent field lines that builds tension. Sometimes scientists observe what's called flux emergence, where new magnetic field rises up from below the sun's surface and interacts with the existing field structure, adding new energy and complexity to the system. Other times they see the formation of magnetic structures called filaments, or prominences, long, thin arcs of plasma, held suspended above the sun's surface by magnetic fields. When these structures become unstable, when the magnetic support fails, they can erupt and trigger a coronal mass ejection. These are the precursor signs that space weather forecasters watch for constantly. They're not perfect predictors. The sun still holds mysteries we haven't fully solved, and eruptions can sometimes occur with limited warning. But in many cases, these signs give scientists hours or even days of advance indication that an eruption is becoming more likely. And the equipment we have for monitoring these signs has improved dramatically over the past few decades. Satellites positioned between Earth and the Sun provide continuous observations of active regions. Ground-based telescopes with specialized instruments measure magnetic fields on the Sun's surface in exquisite detail. Together, these observation networks create a comprehensive picture of what's happening in any given active region at any given time. So what are those instruments showing for our current sunspot of concern? The region remains active. Its magnetic field hasn't simplified into a stable configuration. Observations continue to show the complexity that preceded last week's eruption. That doesn't automatically mean another eruption is imminent. Predicting the exact timing of solar eruptions remains one of the great challenges in space weather forecasting. But it does mean the capability persists. It means the conditions that allowed the previous eruption to occur haven't gone away. It means scientists have every reason to continue monitoring carefully, watching for any indication that another release of magnetic energy is building. Historical precedent reinforces the concern. Let's look at some examples from past solar cycles. There have been numerous cases where an active region produced a major eruption, then fired again days later with equal or greater intensity. Sometimes the second eruption was actually stronger than the first, because the initial event destabilized the magnetic structure in ways that made subsequent releases more violent. Sometimes a series of eruptions occurred, each one reorganizing the magnetic field and setting up conditions for the next one. Scientists who study space weather long enough see this pattern repeat across different solar cycles, different active regions, different circumstances, but the underlying physics remains the same. Complex magnetic fields can produce multiple eruptions. Past eruptive activity is actually a strong indicator of future eruptive potential from the same region. There's another factor worth considering: the phase of the solar cycle. The Sun goes through an approximately 11-year cycle of activity, oscillating between periods of many sunspots and frequent eruptions, and quieter periods with fewer sunspots and less activity. Right now, we're in an active phase of the solar cycle. The Sun's magnetic field is complex and dynamic. Sunspots are appearing regularly. Eruptions are common. This is the environment in which regions like our current sunspot of concern thrive. It's the kind of solar activity level where repeat eruptions from active regions are not just possible but relatively common. Scientists expect to see multiple significant space weather events throughout this active phase. The question is never will there be more eruptions? There will be. The question is which regions will produce them and when. Right now, we have an identified region with proven capability, still aimed at Earth, still showing magnetic complexity during an active phase of the solar cycle. From a space weather forecasting perspective, this is exactly the kind of situation that warrants continued careful attention, informed scientific monitoring and recognition that the conditions are present for another significant event. Scientists have refined their watching brief. They're monitoring this region more closely than the various other sunspots currently visible on the Sun, because this one has already demonstrated what it can do. They're analyzing the magnetic field data multiple times per day. They're looking for any precursor signs that would indicate an eruption is becoming more likely. They're keeping space weather forecasts updated with the latest assessment of the situation, and importantly, they're communicating clearly about what they're seeing and why it matters. Space weather forecasting has matured significantly over the past few decades. We're better at monitoring, better at analyzing, better at predicting than we've ever been before. We're not perfect, the Sun still surprises us sometimes, but we're capable of providing meaningful warning and meaningful context for ongoing situations like this one. When scientists say they're watching an active region carefully because it could erupt again, that's not fear-mongering. That's professional assessment based on observed characteristics, historical patterns, and current monitoring data. It's the appropriate response to a real, ongoing situation that could develop further at any time. Whether that development actually occurs, whether this sunspot produces another significant eruption before rotating out of Earth-facing position, that's what we're all waiting to see. And the monitoring continues around the clock, watching for any sign that the Sun is preparing to demonstrate its power once again. While most of the world went back to daily routines, after last week's aurora displays faded, a different kind of attention continued in observatories, space weather centers, and monitoring facilities around the globe. Scientists didn't move on. They couldn't, because the source of that storm remained visible, active, and worthy of continued observation. So what exactly are they seeing? What does the monitoring process actually look like? And what can current data tell us about whether another eruption is building or the danger is gradually subsiding? Let's pull back the curtain on the space weather monitoring network and understand what's happening in real time as scientists track this situation. Space weather monitoring has become a sophisticated global enterprise over the past several decades. It's not one person with one telescope watching the Sun. It's a coordinated network of instruments, satellites, observatories, and analysis centers working together to maintain continuous surveillance of solar activity. The Sun never sleeps, and neither does the monitoring network. 24 hours a day, 7 days a week, instruments are gathering data, computers are processing observations, and scientists are analyzing the results. When an active region like our current sunspot of concern appears and demonstrates significant capability, it becomes a focal point for that entire network. The most crucial observations come from satellites positioned at a special location in space called the First Lagrange Point, a spot about 1 million miles from Earth, directly between our planet and the Sun, where the gravitational pull of Earth and Sun balance in a way that allows a satellite to maintain a stable position with minimal fuel expenditure. Several spacecraft occupy this orbital location, and their mission is singular: watch the Sun constantly, gather data about solar activity, and provide early warning of anything heading toward Earth. These satellites carry multiple instruments designed to observe different aspects of solar behavior. Some measure the sun's magnetic field, others monitor for X-ray and ultraviolet emissions that spike during eruptions. Still others image the sun in various wavelengths, creating a comprehensive picture of what's happening on its surface and in its atmosphere. When these satellites observed our sunspot of concern last week, they detected all the characteristic signatures of a major eruption. They saw the magnetic field reconfiguration. They observed the X-ray spike as plasma heated to extreme temperatures during the eruption. They tracked the coronal mass ejection as it lifted off from the sun's surface and began its journey toward Earth. And crucially, they didn't stop watching after that eruption. The instruments continued monitoring the active region, gathering data about its magnetic field structure, its emission patterns, any signs of continued activity or developing instability. That ongoing monitoring is what provides the current assessment of the situation. Ground-based observatories complement the satellite observations. Multiple facilities around the world operate telescopes specifically designed to observe the sun safely and measure its magnetic field in detail. These instruments use specialized techniques to analyze light coming from the sun, breaking it down into its component wavelengths and looking for the signatures of magnetic fields in the specific patterns of those wavelengths. It's complex physics, but the result is remarkably detailed maps of the magnetic field structure across the sun's surface. Scientists can see not just where magnetic fields exist, but how strong they are, what direction they're pointing, how they're organized, and how they're changing over time. When you combine satellite data with ground-based observations, you get a comprehensive picture of an active region's current state and evolution. For our sunspot of concern, that combined dataset shows a region that remains magnetically complex even after last week's eruption. The magnetic field hasn't simplified into a stable two-pole configuration. Multiple poles still interact. Field lines remain twisted and stressed. The kind of magnetic shearing that often precedes eruptions continues to be present in the data. All of these are signs that the region retains eruptive potential, that the conditions which allowed last week's eruption to occur haven't fundamentally changed. But monitoring isn't just about static measurements of current conditions. It's also about tracking changes over time, watching for trends that might indicate something new is developing. Scientists compare today's observations with yesterday's, look for differences, analyze whether the magnetic field is becoming more stressed or less stressed, whether new activity is emerging or existing activity is declining. They watch for specific precursor signs that historically appear hours to days before major eruptions increasing magnetic shear, flux emergence, formation of unstable filament structures, changes in the active region's X-ray or ultraviolet emission patterns. This is where space weather forecasting becomes as much art as science. The data provides information, but interpreting that information, judging whether it indicates increased eruption likelihood or just normal variation, determining whether conditions are stable or trending toward instability, these require experience, judgment, and an understanding of how the sun behaves that comes from years of observation. Senior space weather forecasters have watched hundreds of active regions throughout multiple solar cycles. They've seen which signs reliably precede eruptions and which turn out to be false alarms. They've learned to read the subtle patterns in the data that distinguish a region that's settling down from one that's building toward another outburst. Current assessments, based on the latest available data as we move through late January, indicate that the sunspot remains active but hasn't yet shown definitive signs of imminent eruption. That's a careful, measured statement that reflects both the ongoing capability and the uncertainty inherent in solar eruption prediction. The region could erupt again at any time the conditions are present for that to happen. But there's no guarantee it will, and there's no way to predict exact timing with confidence. It's a situation that requires continued vigilance without necessarily triggering alarm bells. Watch and wait, monitor and analyze. Stay prepared for the possibility while recognizing that many possibilities never materialize into actual events. Scientists also pay attention to the broader context of solar activity. Our sunspot of concern isn't the only active region currently visible on the sun. Several other sunspots occupy various positions on the solar disk, each with its own characteristics, its own level of activity, its own potential for eruptions. Some are small and simple, unlikely to produce anything significant. Others show complexity worth monitoring. Space weather forecasters track all of them simultaneously, maintaining awareness of the complete picture, even while focusing particular attention on the regions that pose the most immediate concern. It's a complex juggling act, staying current with multiple evolving situations while ensuring that the most significant threats receive appropriate scrutiny. The international nature of space weather monitoring deserves emphasis. This isn't one country or one agency working in isolation. Scientists around the world share data, coordinate observations, and collaborate on analysis. When an American satellite detects something significant, scientists in Europe, Asia, and elsewhere have access to that data within minutes. When a ground-based observatory in Japan makes detailed measurements of a sunspot's magnetic field, forecasters at prediction centers in the United States incorporate that information into their assessments. This global cooperation ensures that monitoring continues uninterrupted, that multiple perspectives inform the analysis, and that warnings reach all affected parties regardless of geographic boundaries. For our current situation, that global network provides comprehensive coverage. The sunspot is being watched continuously by multiple instruments with different capabilities, operated by different agencies, analysed by scientists with different specialties and perspectives. If precursor signs of another eruption emerge, they'll be detected quickly by multiple independent observers. If the region's behaviour changes significantly, forecasters will update their assessments and communicate those updates to anyone who needs to know. The monitoring infrastructure is robust, capable, and focused on this situation. But all the sophisticated instruments and expert analysis in the world can't eliminate the fundamental uncertainty inherent in solar eruption prediction. The Sun is a complex dynamic system operating under extreme conditions we can't fully replicate in laboratories. The physics of magnetic field reconnection, the process that triggers most solar eruptions, involves phenomena at multiple scales. From the vast structures visible in satellite images down to microscopic interactions between particles. We understand the broad outlines of how it works, but the detailed prediction of exactly when and how a particular active region will erupt remains beyond our current capability. We're better at it than we were a decade ago, and we'll be better at it a decade from now than we are today. But for this moment, for this sunspot, there's irreducible uncertainty. What scientists can say with confidence is this: the region remains capable of erupting. The magnetic complexity persists. The Earth-facing position continues for several more days. The monitoring is ongoing. The data shows no definitive signs of imminent eruption, but also no indication that the danger has passed. It's an active situation that could remain quiet, could produce minor activity, or could generate another significant eruption similar to or stronger than what we experienced last week. All of those outcomes remain possible, and until the sunspot rotates safely out of Earth-facing position, the watching continues, the analysis goes on, the preparedness remains in place. Because if there's one lesson scientists have learned from decades of space weather observation, it's this: the Sun is capable of surprise, and complacency is never appropriate when dealing with an active region that has already proven what it can do. That brings us to the question every viewer is probably wondering by now: what would it actually mean if this sunspot does erupt again? What would happen here on Earth if another powerful blast of solar material reaches our planet? That's where we need to turn our attention next to the potential impacts, the vulnerabilities, and the preparedness that stands between a solar eruption and serious consequences for our technological civilization. Understanding that a sunspot could erupt again is one thing. Grasping what that eruption would actually mean for Earth, for our technology, for our daily lives, that's where the story becomes personal, where the abstract science transforms into concrete concern. So let's be clear and honest about what's at stake if this sunspot produces another powerful eruption before rotating out of Earth-facing position. Not to create fear, not to suggest severe disruption is inevitable, but to understand realistically what impacts are possible and how our modern society might experience another severe geomagnetic storm. You'll start with the most visible effect, the one most people think of when they hear about solar storms: auroras. When charged particles from a solar eruption interact with Earth's magnetic field and atmosphere, they create those spectacular displays of coloured light dancing across the sky. In a severe storm like last week's, auroras appear far beyond their normal polar regions. People in areas that rarely or never see northern lights suddenly find their night sky alive with green, red, and sometimes purple curtains of light. It's beautiful, undeniably, and it's one of the few positive aspects of a significant geomagnetic storm. If another eruption reaches Earth with similar intensity, we'd likely see another round of aurora displays at unusual latitudes. For millions of people, It would be a once-in-a-lifetime viewing opportunity. But the auroras are just the most visible symptom of much deeper effects occurring throughout Earth's magnetic environment. When a powerful blast of solar plasma slams into our planet's magnetic field, it doesn't just create pretty lights, it fundamentally disturbs the entire magnetosphere, that protective magnetic bubble surrounding Earth that shields us from the constant stream of particles flowing from the Sun. The magnetosphere compresses on the side facing the Sun, distorts dramatically, and gets pumped full of enormous amounts of energy. That energy has to go somewhere, and where it goes determines what impacts we experience. Satellites are among the most vulnerable components of our modern infrastructure during severe geomagnetic storms. These spacecraft orbit Earth in an environment that becomes significantly more hostile during magnetic storms. The density of particles increases dramatically in the region where many satellites operate. That increased density creates drag-actual atmospheric resistance even at orbital altitudes that affects satellite trajectories. During particularly severe storms, satellites can lose altitude, requiring fuel-consuming correction maneuvers or risking premature re-entry. The energetic particles streaming through the magnetosphere can also cause direct damage to satellite electronics. They can create false signals, trigger computer errors, degrade solar panels, and in extreme cases cause permanent damage that shortens a satellite's operational life or ends it entirely. Think about how much we depend on satellites today. Weather forecasting relies on satellite observations, global positioning systems that guide everything from your smartphone's navigation app to commercial aircraft and shipping routes. Those are satellite-based. Communication networks, especially in remote regions, depend on satellite relays. Television broadcasts, internet connectivity in underserved areas, military and intelligence operations satellites are woven throughout the fabric of modern civilization in ways most people never think about. When a severe geomagnetic storm degrades satellite operations or damages spacecraft, those impacts ripple through multiple systems simultaneously. Communication disruptions extend beyond satellites. Radio waves traveling through Earth's atmosphere get affected by the charged, magnetically disturbed layers of the ionosphere during geomagnetic storms. High-frequency radio communications, the kind used by aircraft flying over polar regions, by ships at sea, by emergency services in remote areas, can become unreliable or completely disrupted. Aviation faces particular challenges because polar routes depend heavily on radio communication with ground control. During severe storms, airlines often reroute flights away from polar regions to maintain reliable communication and avoid the increased radiation exposure that occurs at high altitudes during magnetic storms. Those reroutes burn extra fuel, add travel time, and create logistical complications across the aviation network. And GPS accuracy suffers during magnetic storms because the signals traveling from satellites to receivers on Earth have to pass through the ionosphere, and when that ionosphere is charged and disturbed, the signals get delayed and distorted in unpredictable ways. For most casual users, a few meters of GPS error might not matter much, but for applications that require precision aircraft navigation during approaches and landings, autonomous vehicles, precision agriculture, surveying, timing systems that synchronize financial transactions, and power grid operations, GPS degradation during severe storms can create real problems that require backup systems and careful monitoring. Perhaps the most concerning potential impact involves electrical power grids. This is where severe geomagnetic storms can transition from inconvenience to serious infrastructure threat. Here's how it works. When the magnetosphere gets disturbed and all that energy starts flowing around, it creates rapidly changing magnetic fields around Earth. Those changing magnetic fields can induce electrical currents in long conductors on the ground, like the high-voltage transmission lines that form the backbone of power grids. These induced currents, called geomagnetically induced currents, flow through the power grid infrastructure where they don't belong, creating additional stress on transformers and other equipment designed to handle specific electrical loads. The danger isn't just theoretical. History provides a dramatic example. In March of the late 20th century, a severe geomagnetic storm induced currents powerful enough to cause a cascade failure in Quebec's power grid, causing a power outage affecting millions of people for hours during winter. The storm damaged transformers, created voltage instabilities, and demonstrated clearly that modern power grids are vulnerable to severe space weather. And here's the concerning part. Power grids have become more interconnected and more complex in the decades since that event. More dependency, more connectivity, potentially more vulnerability. Engineers and grid operators are aware of these risks. Protective systems have been implemented. Monitoring and response procedures have been developed. But the fundamental physics hasn't changed. Severe geomagnetic storms can induce problematic currents in electrical infrastructure, and the more severe the storm, the greater the potential for impacts. Now let's be clear about probabilities and context. Not every geomagnetic storm causes power outages. Not every severe storm leads to significant satellite damage. The impacts depend on multiple factors: the exact orientation of the magnetic field embedded in the solar eruption, how directly it strikes Earth's magnetosphere, the local time and season when it arrives, the specific vulnerabilities of affected systems at that moment. Last week's storm caused some satellite disruptions, some communication difficulties, some GPS degradation, but no widespread power failures, no catastrophic damage. It was significant, yes, but manageable. Our systems handled it. If this sunspot erupts again with similar intensity, we'd likely see similar impacts. Aurora displays at unusual latitudes. Temporary satellite disruptions, communication challenges in some regions, GPS accuracy degradation, power grid operators monitoring their systems carefully and taking protective measures if needed. It would be an event worth paying attention to, worth preparing for, but not necessarily catastrophic. The infrastructure we've built, the protective systems we've implemented, the monitoring networks that provide warning, these exist precisely to help us manage events like this. But, and this is important, there's always the possibility of a stronger event. Solar eruptions vary in intensity. Last week's was severe by the classification system scientists use, but it wasn't the most extreme category. Storms can be stronger. History shows us that the Sun is capable of producing eruptions significantly more powerful than what we experienced last week. The magnetic complexity in this particular sunspot, the energy storage visible in its structure, the demonstrated capability it's already shown, these factors mean another eruption could potentially be stronger rather than weaker. Not guaranteed, but possible. And if a more powerful eruption occurred, if it reached Earth with optimal magnetic orientation for creating impacts, then the effects would be proportionally greater. More satellite disruptions, more communication challenges, greater stress on power grid infrastructure, more widespread and longer-lasting impacts. This is why space weather forecasting matters. This is why scientists monitor active regions carefully and issue warnings when significant eruptions occur or appear likely. It's not about creating panic. It's about providing information that allows operators of vulnerable systems to take protective measures, to increase monitoring, to prepare backup systems, to be ready to respond if impacts occur. Modern society runs on infrastructure that's more capable, but also more complex and more interdependent than ever before. A disruption in one system can cascade into others. A satellite failure can affect communication networks. Communication problems can impact aviation safety. GPS degradation can affect timing systems that keep financial markets synchronized. Everything connects to everything else. Which means space weather events that might have been minor inconveniences a few decades ago can create more far-reaching effects today. But here's the empowering part of this story. We're not helpless. We're not sitting blind and vulnerable waiting for the sun to wreak havoc. We've built monitoring systems specifically to track space weather. We've developed protective systems for satellites. We've implemented procedures for power grid management during magnetic storms. We've created communication networks with redundancy and backup systems. We've studied the vulnerabilities and taken steps to mitigate them. Perfect protection isn't possible. We can't put a shield around Earth to deflect solar eruptions, but we can monitor, prepare, and respond intelligently. That capability has improved dramatically over recent decades and continues to improve. So if this sunspot does erupt again, if another powerful blast of solar material heads toward Earth, we won't be caught completely off guard. We'll have warning measured in hours or days. We'll have time to alert satellite operators, to notify power grid managers, to inform airlines and communication networks. We'll be able to watch the eruption cross space, track its progress, calculate its arrival time, and prepare accordingly. The impacts might still occur, physics is physics, and severe storms can affect our systems despite our best preparations. But we'll face them with awareness, with readiness, with systems designed to handle the stress and recover quickly. This is the balance we need to understand. Real vulnerability exists. Real impacts are possible, but real capabilities for management and response also exist. The sun is powerful, yes, but we're not powerless. Knowledge, monitoring, preparation, these matter. They transform space weather from unpredictable threat to manageable risk. And as we continue watching this sunspot, as scientists track its position and monitor for signs of another eruption, that entire infrastructure of observation and preparedness stands ready to do exactly what it was designed for, to help us navigate the sometimes stormy space environment in which our planet exists. By now, you understand what happened last week. You know the sunspot is still there and still capable, and you grasp what another eruption could mean. But there's one question probably occupying your thoughts right now. When will we actually know if it's going to happen again? How long do we wait in this state of possibility? Is there a definitive timeline after which we can relax, confident the danger has passed? Let's address that uncertainty head-on, because understanding both what we can predict and what we can't is essential to making sense of this situation. Solar eruption prediction remains one of the great challenges in space science. Despite decades of study, despite sophisticated instruments monitoring the sun constantly, despite our improving understanding of the underlying physics, scientists still cannot predict with certainty exactly when a specific sunspot will erupt. We can identify which regions are capable of erupting that part we're relatively good at. We can sometimes see precursor signs hours or days before an eruption that increase the probability assessment. We can calculate trajectories once an eruption has occurred and estimate arrival times at Earth, but predicting the exact moment when a specific active region will release its magnetic energy, that capability still eludes us. Think about earthquake prediction as an analogy. Seismologists can identify which fault lines are under stress, which regions face higher earthquake risk, which areas should prepare for the possibility. They can measure strain building in the Earth's crust. They can study historical patterns. But they can't tell you that an earthquake will occur at precisely 3 p.m. next Thursday. Solar eruptions operate under similar constraints. We know the conditions that make eruptions likely. We watch for warning signs, but the exact trigger mechanism, the precise moment when magnetic instability crosses the threshold from stressed to catastrophically unstable, that remains unpredictable at our current level of understanding. What scientists can do, what they're doing right now for this sunspot, is provide probabilistic assessments. Instead of saying an eruption will occur at this time, they say, based on current observations, the probability of a significant eruption from this region over the next 24 hours is X%. Those probabilities get updated as new data comes in, as the active region evolves, as monitoring continues. It's not perfect certainty, but it's useful information that helps people make informed decisions about preparedness and response. For our current situation, the critical timeline isn't determined by eruption prediction, it's determined by solar rotation. Remember that Earth-facing window we discussed earlier? That's the key timeline everyone is tracking. Right now, in late January, this sunspot remains in Earth-facing position with several days left before rotation carries it around the sun's western limb and onto the far side. Each day that passes, each rotation of the sun brings us closer to the point where the sunspot's position no longer matters from an Earth impact perspective. Scientists can calculate that timeline with reasonable precision. They know approximately when the active region will rotate out of the Earth-facing zone. That becomes the natural deadline for this particular concern. If the sunspot reaches that rotation point without producing another significant eruption, does that mean the danger was overblown, that the concern was unnecessary? Not at all. It means we watched a capable, active region during the period when it could affect Earth, and fortunately nothing happened. That's actually the most common outcome when scientists monitor potentially dangerous sunspots. Most of them don't produce major eruptions during their Earth-facing transit, even when they have the capability to do so. The watching wasn't wasted effort, it was appropriate vigilance during a period of elevated possibility. Just because the worst case doesn't materialize doesn't mean the precaution was unjustified. But while we're waiting for that rotation deadline to arrive, how do we live with the uncertainty? How do we balance awareness of the possibility against getting on with daily life? This is where the honest acknowledgement of limits becomes important. Scientists don't know if this sunspot will erupt again before rotating away. They know it could. They know it has the capability. They're monitoring carefully for any signs that an eruption is becoming more likely, but they can't guarantee one way or the other, and that uncertainty is okay. It's the reality of dealing with complex natural systems that don't follow perfectly predictable patterns. Space weather forecasting centers issue regular updates about ongoing situations like this. They publish forecasts typically looking ahead over 3-day periods assessing the likelihood of various levels of solar activity. They maintain a classification system for space weather similar to the way terrestrial weather services have categories for hurricanes or winter storms that helps communicate the potential severity of events. When monitoring shows increased probability of significant activity, forecasts get updated and alerts get issued to organizations that need to take protective measures. This communication infrastructure exists specifically to bridge the gap between scientific uncertainty and practical decision-making. We can't predict exactly, but we can inform meaningfully. For individuals watching this situation, wondering whether another storm is coming, the practical reality is this: there's nothing you need to do differently in your daily life. Solar storms don't pose direct danger to people on Earth's surface. Our atmosphere protects us from the radiation. Our magnetic field deflects the charged particles. The impacts, as we discussed, affect technology and infrastructure, satellites, communications, power grids, but those are managed by professionals who monitor space weather alerts and respond accordingly. Your awareness is valuable for understanding the world around you, for appreciating the dynamic relationship between Earth and Sun, for recognizing that space weather is a real factor in our technological civilization. But it doesn't require personal action beyond staying informed. That said, if you're someone who depends on systems potentially affected by space weather, if you operate satellites, manage power grid infrastructure, fly aircraft over polar routes, you should rely on high-precision GPS for critical operations, then space weather awareness becomes professionally important. Those professionals do monitor the forecasts, do adjust operations based on space weather conditions, do implement protective measures during severe storms. For them, the uncertainty isn't paralyzing, it's managed through probabilistic decision-making, backup systems and established procedures for responding to various scenarios. As we move through the coming days, as this sunspot continues its rotation across the sun's face, the situation will evolve in one of several possible directions. Maybe the region will produce another eruption, perhaps even stronger than last week's, and we'll face another round of impacts and spectacular auroras. Maybe it will produce minor activity that doesn't significantly affect Earth. Maybe it will remain quiet, gradually rotating out of Earth-facing position without further drama. All of those outcomes are possible. Scientists will continue monitoring regardless, tracking the region's evolution, analyzing the data, updating their assessments. And when the sunspot finally does rotate around to the far side of the sun, when it's no longer aimed at Earth, the focused attention will diminish. It won't disappear entirely. Scientists will still track the region as it rotates around the back and eventually returns to Earth view in a couple of weeks, but the immediate concern will have passed. This is the rhythm of space weather monitoring. Periods of heightened attention when active regions appear in Earth-facing position and show concerning characteristics. Careful watching during those periods. Then relaxation of alert status as regions rotate away or quiet down. Then renewed attention when new active regions emerge or previously quiet regions suddenly activate. It's continuous, ongoing, necessary work that happens largely behind the scenes, while most of the world focuses on other concerns. But when situations like our current one develop, when a region proves its capability through action and remains positioned to act again, that monitoring work becomes directly relevant to understanding what might happen next. So we wait, we watch. Scientists continue their observations, space weather forecasters maintain their assessments, and the sunspot continues its rotation, each day bringing us closer to resolution one way or another. The uncertainty won't last forever. Solar rotation guarantees that. Within days, the situation will have evolved into a new phase, whether that's recovery from another eruption, relief that the window closed without incident, or something in between. Until then, the waiting continues, accompanied by the best monitoring and analysis humanity can provide. And as we wait, there's a bigger picture worth considering, a broader perspective on what this situation teaches us about our relationship with the star that powers our world. That's where we need to turn our attention now as we bring this journey to its conclusion. We've travelled through the science, the monitoring, the possibilities, and the uncertainties together. We've explored what happened last week, why it matters that the sunspot is still there, what scientists are seeing in their continuous observations, and what another eruption could mean for our technological civilization. We've confronted the unpredictability, acknowledged the real vulnerabilities, and recognized the real capabilities we've developed to manage space weather impacts. But before we part ways, before you move on to whatever comes next in your day, let's step back and consider what this entire situation reveals about something larger, about our relationship with the Sun, about our place in the solar system, about the balance between vulnerability and resilience that defines modern civilization. The Sun is the reason Earth exists as a habitable world. Every bit of energy that drives our weather, that enables photosynthesis, that ultimately powers human civilization. It all comes from that massive fusion reactor in the sky. We orbit at exactly the right distance to receive life-sustaining warmth without being scorched. We bask in the light that makes our world visible and beautiful. We depend absolutely, fundamentally, inescapably on the Sun's steady output of energy. But that same Sun, that life-giving star, is also a dynamic, powerful, occasionally violent entity. It erupts, it flares, it sends blasts of plasma and radiation streaming across the solar system. And when we happen to be in the path of those eruptions, we feel the effects despite being separated from our star by the vast gulf of space. This duality, the Sun as both benefactor and threat, reflects a broader truth about our existence. We've built an extraordinary civilization, one that depends on sophisticated technology, interconnected systems, and infrastructure of remarkable complexity. That technology gives us capabilities our ancestors couldn't have imagined. Communication across any distance, navigation with precision measured in meters, power generation and distribution that lights our nights and runs our machines, satellites that orbit Earth providing services we've come to consider essential. But that same technological sophistication creates vulnerabilities. Our systems are amazing when they work, but they're also exposed to forces and phenomena most people never think about. Space weather is one of those phenomena invisible to direct experience, absent from daily awareness, yet real and occasionally impactful. What this sunspot, this ongoing situation we've been exploring together, really represents is a reminder that we live in a dynamic universe, not a static one. A reminder that our planet exists in a space environment with its own weather patterns and storms. A reminder that the technologies we depend on operate in conditions we don't directly perceive, but that scientists monitor constantly. It's a reminder that for all our capabilities we remain subject to forces beyond our control. We can't tell the Sun when to erupt or when to stay quiet. We can't eliminate the vulnerability of satellites to energetic particles. We can't make Earth's magnetic field impervious to disturbance. But we can observe, understand, prepare, and respond intelligently. That's the power we actually have, and it's not insignificant. Throughout this situation, from last week's initial eruption through the ongoing monitoring of the sunspot that remains aimed at Earth, the space weather forecasting community has demonstrated exactly that capability. They detected the eruption quickly. They calculated its trajectory and speed. They issued warnings with enough lead time for protective measures to be implemented. They tracked the impacts as the storm arrived. They continued monitoring the source region, providing updated assessments as new data became available. They communicated clearly about what was happening, what might happen next, and what it all means. This is expertise in action, institutional knowledge built over decades of observation and experience, infrastructure created specifically to bridge the gap between solar behavior and human preparedness. It's not perfect, no human system is, but it's remarkably capable and continually improving. As we stand now, in this moment of ongoing possibility where the sunspot remains active and Earth-facing with days left in the critical window, we're living in what space weather scientists call an elevated watch period. Nothing has happened since last week's storm. The Sun hasn't erupted again from this region. But the capability persists, the position remains threatening, and the monitoring continues. Each day without an eruption is one day closer to the sunspot rotating safely away. Each observation session provides new data about the region's magnetic state and activity level. Each forecast update refines our understanding of the current situation. It's science and vigilance working together to maintain awareness during a period when awareness matters. Will this sunspot erupt again before it rotates out of Earth-facing position? Honestly, we don't know. Scientists are watching, analysing, prepared to detect any precursor signs and issue warnings if another eruption appears imminent. But prediction remains imperfect. The sunspot could fire another powerful blast toward Earth tomorrow. It could remain quiet for the rest of its Earth-facing transit. It could produce minor activity that doesn't significantly impact our planet. All of those outcomes are possible, and we won't know which actually occurs until we're living through it. That uncertainty is uncomfortable for people who prefer definitive answers, but it's the honest reality of dealing with complex natural systems. What we can say with confidence is this: regardless of what happens with this specific sunspot over the next several days, the broader pattern continues. The Sun will produce more eruptions. More active regions will appear. More space weather events will affect Earth. This is normal, ongoing, part of living on a planet orbiting an active star during a phase of its activity cycle. We'll face situations like this again, maybe this year, maybe next year, maybe in the years that follow. Each time, scientists will monitor, forecasters will assess, operators of vulnerable systems will take appropriate precautions. Society will manage the impacts and continue functioning, because that's what we've learned to do, not to prevent space weather, which is impossible, but to live with it intelligently. There's something almost profound in that accommodation. We can't change the sun, we can't control space weather, but we can observe it, understand it, prepare for it, and adapt to it. That's a form of relationship, or a way of coexisting with forces larger than ourselves. Our ancestors saw the sun as a god, incomprehensible and all-powerful. We see it as a physical object governed by natural laws, still powerful but understandable through science. That shift in perspective from mystery to knowledge represents one of humanity's great achievements, and that knowledge, imperfect as it remains, gives us agency. Not control, but agency, the ability to make informed decisions, to take meaningful actions, to protect what we've built while acknowledging the limits of that protection. So as you move forward from watching this, as you return to your daily life while scientists continue their vigil over this active sunspot, carry with you an awareness of that larger context. We live in a remarkable time when humans can watch the sun constantly. Our wall can detect eruptions as they happen, can track solar material as it crosses space toward Earth, can prepare for impacts before they occur. That's extraordinary when you think about it. But we also live in a time of genuine vulnerability, when our technological civilization depends on systems exposed to space weather effects we can't prevent. That's sobering and requires ongoing attention. The story of this sunspot from its first eruption last week, through the realization that it's still there and still active, to the ongoing monitoring and uncertainty about what comes next, is ultimately a story about that balance: capability and vulnerability, knowledge and uncertainty, preparation and acceptance. It's a very human story about how we navigate a universe that doesn't always cooperate with our preferences, but can be understood well enough to make our way through it successfully. Thank you for staying with me through this exploration. If you found value in understanding this situation more deeply, if you appreciate having context for what's actually happening rather than just seeing scattered headlines, then do me a favor. Hit that like button to help this information reach others who care about understanding the real science behind space weather events. Subscribe to this channel so you stay informed about developments in this story and other science topics that affect our world in ways both visible and invisible. And drop a comment sharing where you're watching from. I'm genuinely curious to know how widely distributed this audience is, how many different parts of Earth are looking up at the same sun and wondering what it will do next. The monitoring continues, the sunspot remains, the scientists watch, and we all wait together to see what our star decides to do in the days ahead. Whatever happens, we'll face it with the best tools humanity has developed for understanding and managing our relationship with the sun. That's not perfect protection, but it's something real, something valuable, something worth appreciating. The universe doesn't owe us safety, but we've built systems to create resilience. That's our part of the story, and it continues day after day as we orbit our sometimes stormy star.